Okay, hi everyone. We're very excited to have David Espinosa back with us for the third time.
Second.
Oh, only the second. The second Berkeley Seminar to hear some exciting stuff about monads. David, whenever you're ready.
Okay. Oh boy. All right. Let's see. So who's actually excited about like monad composition? Is that a area? Maybe a couple? I'm curious. Because this is a talk that I'm in danger of being the only one excited about. But, okay, but we'll see. Okay, and I want to be somewhat interactive with you guys, but there is time pressure and I always pick up too much material maybe. So we'll have to see how that goes. All right, because I'm also in danger of giving this thing at like lightning talk speed. So I think there's about, I don't know, we could sort of say 4 parts to it. And I'll tell you what they are. The first part is about a monad that you maybe haven't heard about, which I'm calling the parallel prefix monad. It's also maybe the carry look-ahead monad. And it doesn't really belong with the other parts, but I felt like talking about it because it's not very well known. The next part is about monad translation compose, and that's maybe the meat of the thing. The one after that is there's some previous work by Andrei Felinsky on sort of monads and continuations. Has anyone read any papers of Andrei's on that? There's one representing monads and there's another representing layered monads. And representing monads isn't too hard. Representing layered monads is hard. And I'm going to sort of explain to you how that one goes just for entertainment. And the last part is a miscellaneous that you guys can be interactive on, sort of catch-all session on all kinds of random topics, which I think I'm expecting you guys to like that part more than the other parts. But let's see. Okay, so here we go. So one thing that monads can do is they're good at tree traversals. And we can talk about information being passed up, being passed down, and being passed through. Do you recognize those monads? What are the usual names for those 3 monads? First, second, and third ones.
First 2 are writer and reader.
And the last one is? State. Writer, reader, state. Okay? And so here's a new one. This is a prefix sum monad. And essentially information flows up like the same way that writer does, and information flows down, which is the sum of everything to the left. Okay?
I feel like I don't want to get lost now.
Oh, it's not cumulative. It doesn't matter.
Well, I just can you say a little bit about how you think about a monad? Or I'm not a Haskell programmer.
Sure, it's an abstraction of an imperative language that you can embed into functional language.
Could you maybe explain how write and read are monads?
No. But the abstraction of the imperative language is by abstracting return and let, which are not the things that you would have expected. But let is kind of like sequencing, and return is kind of like what is it, a unit kind of thing. Okay, but you'll catch on. So there's my return and let for this one. And so here's an example. We're just going to traverse a tree. And at every leaf node over here, I generally, in this talk, I'm putting important things in red because there's a lot of information on a slide. So I'm not going to really give you time to read the whole slide. So just read the red part. That's the sort of clue for the talk. So at a leaf, we will, what will we do? We'll return, we'll leave the leaf as it is. That's the part on the left. And we'll just, what we do? Let me look, which way did I write it? I don't know. So we are going to put in the leaf, we're going to put the sum of all the things to the left, okay? And I started that sum at 1 just for entertainment, just to be difficult. You would normally start at 0. Okay, so what's to the left of 3? It's whatever we started with, we'll put a 1. What's to the left of 2? It's the 1 plus the 3. Okay, what's to the left of the 6? The 1 plus the 3 plus the 2. And that's what we'll put. Okay? And what we're getting passed up is the sum of everything below, which is 3 plus 2 plus 8. Okay? So that's how this monad goes. What can you do with it? You can do a number of things. You could do a fast multiplication. Here's an example. Okay, you're not expected to read this now. You could do a carry look ahead adder. That's a kind of homework. Let me see if
What sense of fast multiplication do you mean there? You mean like
log time.
Yeah.
Like, yeah. It's usually done with, usually you say fast exponentiation, but I happen to have written, that was parameterized on a monoid, so it was parameterized on a sum monoid rather than a product monoid. If you parameterize on product monoid, you get exponentiation. Okay, so that's just a monad for entertainment. Okay, let's move on. We're done with the first part. So monads don't compose. Suppose you have two monads, S and T, you want to compose them, and you want to write a join, which is the product for your ST. So you want an operator from ST to ST. Okay? And what you have at your disposal to write this operator is you have return for S and T, and I'm thinking of this as maybe string rewriting. So you want to start with a string ST, and you want to get to ST. Okay? And what can you do with this string? Well, you can insert S's and T's, those are the returns. And when you have SS, you can turn that into a single S, or you have TT, you can turn it into a single T. Okay? And you can convince yourself that there's no way in the world that you're going to get from ST to ST. Okay? You're just not. You want a formal proof, you think of an invariant that's maybe non-decreasing, and you get there. Okay? So, but what good's an impossibility proof? It just tells you what constraints you have to violate. So I'm sure we're going to violate some constraints. Okay? So the first idea that would pop into your head that we're not going to discuss is if you had a map from TS to ST, which is called a distributive law. If you had that, then you could get this to work. Okay? So I just wanted to convince you they don't compose. Okay. So now we're going to talk about monad translations. Monad translations. We start with an expression that's basically in a pure language, and we monad translate it, which is goes like this. We just say let A be return 1, let B be return 2, in return A plus B. Okay, and I'm using elet for my monad let and ereturn for my unit. Okay, those are often called bind and unit, but I prefer to call it let because that's kind of what we call it in programming languages.
So is this just the identity monad so far?
You could put any monad in there you want. Okay, so I'm gonna throw in an option monad or maybe monad. Okay, and so now we inline the monad, and now and so you can see what's going on, and now we're back in a pure language. And if we want to, we could do that process again, monad translate. Okay, you have to know how to monad translate this, but that's no big deal. Inline the new monad and keep going. So it's always sort of like from a pure program, and then we add a monad to it, and we're back to a pure program because we inline the monad. Okay, and then we do it again. And so that's kind of the monad translations compose concept. Okay. So it just says we do it again. So now we're going to formalize. Here's a language. I think of languages as abstract data types. I'm also using higher order abstract syntax. My language is a little bit rich because I want to be able to write monads in it, which we're going to see in a minute. Languages as theories is like my host language or my meta language already has syntax. I don't need new syntax. Higher order abstract syntax is like my meta language already has variables. I don't need new variables, right? So if you want to make a language, this is sort of like your quickest path. And this language happens to be untyped, but if you were doing this in Ogda, you could make it typed. Okay. And here's sort of the idea of having a monad over maybe this language of expressions. You can, even though it's untyped, everything is sort of typed in practice. There are no type violations. So if this was Ogdo, we could like maybe make these types explicit. But I'm in ML, so I'm not. Okay.
Question,
Yes.
question here. Do you think of your monads as kind of procedure declarations in a programming language?
I think of them as abstracting an imperative language. And the way that I'm going to abstract my imperative language is I'm going to abstract return and let. That's how I think of them. Okay. The next interesting thing that I'm going to do, and this looks a little bit trivial, but it's actually interesting, is I'm going to say an internal monad in a language L basically takes the language L and hands me back a monad where the type of expressions for my monad is the expressions of L. And so what this is essentially a monad that I've written in L, and it's kind of, how do we say, parametric over L, or parameterized by L. Okay, so it can be applied sort of to any L, and that's how I'm going to do my layering. Okay, so let's have an example. Here's the option monad. Okay, and what is this in contrast to? This is in contrast to writing the monad in my host language. Like if you saw some of, say, Wadler's papers, what is it, Essence of Functional Programming or Imperative Functional Programming, say the monad is on, say, the Haskell category. It's written in the meta language. This one is written in my object language. Okay, I'm taking a language L, which we saw had a bunch of operators, and I'm writing my monad over L. Okay, so instead of using like ML option over here in my return, I'm injecting on the left using injection in L. Okay, so that's what's different here. And I'm implementing a few operators to use the monad, but don't pay any attention to that. Okay. And similarly, when I have my let, I'm using case in L, application in L, lambda in L, injection on the right in L. Okay? And what I'm going to do is I'm going to start with a very simple implementation of L, simplest one you could think of, practically the identity. You could make it yourself. And I'm going to start basically adding these monads to it. Okay? And so how do I do that? I do that by monad translation. So the first thing that I do is I take my internal monad and I apply it to L, and that gives me an implementation of the monad. I'm using ML module system here, but it's just a language of theory, so it should be very easy to understand. Okay? And then I do what's basically ordinary monad translation. So for example, my old implementation of int was L.int, which was presumably identity. My new implementation just is TE return of L.int. So what did that E return do? It just did injection on the left. Okay? So this is straight out of Mojian 89 monad translation. It's just like language over a monad. If you've ever seen a monadic interpreter of any kind, this is what you would write. Okay? So to do the whole language, it's just 2 slides. If you've ever seen it, it's no problem. And that's enough to layer these. We can extend by different monads. And so this captures the idea that monad translations compose. And this is just an example I borrowed from one of Felinsky's papers. If you layer on list, state, and resumptions is kind of like interruptible, like yieldable sequences of computations are good for doing interleaving and parallel stuff. Then you can model things like interleavings of different operations on a store. Okay, and I'm not showing you all the code for all of that, but it's an example of what you could do. Okay, so back in about 98, I was talking with John Launchberry, who's a Haskell person, and I said, hey, John, monad translations compose. And he was like, oh, well, that's nice, but there's a problem. And I wonder if you guys might be able to tell the problem, and I'll give you some hints. So I made a monad translation, and I made another monad translation, and I'm essentially composing them because language translations compose, and I'm stacking that up, okay? So I think a lot of people realize that you could do this. Okay. Does that justify the claim monad translations compose?
You have to prove the law is composed.
Well, we have some translations. You might have to prove that any, what is it, semantics that was holding in your language holds after translation. So that would be the instance here. So that's a good point. If your language had some sort of laws for reasoning, you would have to show they hold afterwards.
The monad laws themselves, you also have to prove.
We are not, so we haven't composed any monads, right? We composed language translations. And so that begins to get at the issue. Yeah, Sophie.
Sorry, this is a basic question. I think I got lost about what is, I'm like, all right, monad. Okay, what is a monad translation?
You take a language,
Okay.
and your language before said something like 3 for 3. And that, after translation, becomes inject 3 on the left. And you had something like 3 plus 4. That became like, oh, see if like that first thing threw an exception. Okay, because now the language, you might not just have in left of 3, you might have in right of unit or in right of some exception. And it's like, check the left thing for an exception, check the right thing for an exception. If you got an exception, just return that, return the first one probably. Otherwise, if you got 3 and 4, add them, and then return that on the left. Okay? And you can stack this up with other monads. So if writer monad will let you do output, list monad will let you do sort of non-deterministic operations, things like that. State monad will let you thread things through. Okay. So we're composing translations. Are we composing monad translations? What would that mean? When is the composite of two translations a monad translation as opposed to some other translation? Okay? So in order for it to be a monad translation, what John said was, well, you're composing translations. Of course, language translations compose. But for it to be a monad translation, there has to exist some kind of composite monad, and your translation has to result from translating by that monad in order for your claim that monad translations compose, as opposed to sort of random translations. Okay, so what we need is we need a compose operator that works on these I-monads so that when you extend, which is what we saw, you take L, you extend by S, you extend by T, you would like that to be the extension of L by some kind of resulting monad, right? And this sounds hard because we already proved that monads don't compose. So this compose TS shouldn't really exist. In fact, we proved that it doesn't really exist. Okay, so we should all just go home now. We're done. That was a short talk. Okay? Unless there was, some way to do this. But I looked at the types, like when John and I talked about this in 1998, which was like 25 years ago. Looked at the types, and I just couldn't get it to go through. So I basically gave up for 25 years, but it was bothering me. So I thought maybe, well, why don't I just, at least I can implement this extend thing. That's pretty straightforward, not too hard. Let's see what happens, And I thought a little bit harder and a little bit harder, and, having the code always helps you think. And guess what? You can write it. Okay, so I didn't know that you could write this. So this might be new. Everything else you've seen so far is not new. Okay, parallel prefix monad, but so what? Okay, this could be new. And so what's going on, we'll read the red part. We instantiate IS, okay, which is just our S monad, and we instantiate that on L, okay. We extend L by IS. We instantiate T not on L, but on LS. So we're instantiating T on the language that's been extended by S. Okay? So if L was like a pure language, S was maybe options. LS is a language with options, right? with exceptions. And we don't put T as a monad. T can be put on any language. We don't put it on a pure language. We put it on the exception language or the option language. Okay? And that's enough. If you do that, then you can define return and let for your composite monad in just 2 lines. You won't be able to understand that, but that's what goes on. This is some explanation. So you return for S has type A to SA, that's standard. Return for T, you would think it's A to TA, which is the type that it would have if it were on L. But if it's on L extended by S, everything in this L extended by S is S of something. Okay? And so instead of A to TA, it's SA to STA, which is essentially a monad morphism from S to ST. And at that point, now these compose. Okay? You'd actually be surprised at the order in which they compose, because when you were composing your monads, you were actually thinking they would compose in the other order, but no, it's this. A bit surprising. And where's the magic? The magic is kind of what you can imagine from the translation, which is that T is no longer a black box. Okay? We proved black box monads don't compose. T is no longer a black box. We have the source code for T. So what we're essentially doing is we're taking the source code for T and we're monad translating it by S. And so it's this extra information of having that source code that's letting us do this. That's where the magic is. Okay? And you can do the same thing when T is normally, T would be that type without the S's, but now it's over the S language. It gets S's everywhere, and you can get it to go. Okay. This starts to explain a little bit what's going on in monad transformers. If you start with a monad T and you monad translate it by S, here's what happens in the types. You get an S on the outside, and you also pick up an S at the end of every arrow type, because it's called by value monad translation. So for example, let's say your state monad here, you get an S on the outside, and you also pick up an S at the end of this arrow type. So it's like if you took this type and you applied monad translation to it by S, you would get this. And so these are sort of the monads that you pick up when you do this composition. And you're sort of used to the idea that composition with T is a monad translation, okay, on S. So this is like, it would take S to ST in composition with T. Okay, so this is sort of, everybody knows that sort of the monad transformers come from base monads, and sort of this is how they do it, or one description of how they do it. Okay, let's do the math version of this, because I know you guys are math guys. Given a monad on some category, S on some category, and a monad T on some category, there exists a composite monad on some category. This would be the math version, okay? And I'll tell you the first line, given a monad S on some category C. That was hard. Okay, so S is on C. Where's T? The Kleisli of S. Okay, who agrees? Hands up for Kleisli of S. Any other options? Everybody likes Kleisli of S. Okay, then there exists, let's try the last one. There, I like it. Where's the last one? Where's the composite? Hmm? Back on C. Okay, who thinks back on C and who thinks somewhere else? Eilenberg more categories, or I don't know, you get creative. No? No. Raise your hand if you think it's just C. Okay, all right. Okay, I think it's just C. Okay, batting 1,000. And Barr-and-Wells, Triples, Toposes, and Theories has a chapter sort of at the end. It's called Distributive Laws, and they talk about different maybe ways to do monad translation. Not everybody knows that's there because it's kind of hidden in the back.
Can I ask a question for Kevin? How did you know?
Because David transferred T into the language that had been translated into like S's language, and secretly when computer scientists use a monad, they're in the question category of that monad. And then
That's how you make Kleisler S.
yeah, and then it like just I don't know where else it could be. It would be weird for ST to be on like Kleisler S. It seemed like the composite was just a monad on the side.
Cool. Thanks.
Okay. All right. So one reference is Barr-and-Wells, and I Googled a bit for this, and I found some encouraging things. This is this Stack Overflow or Math Overflow or something, right? And
Hey, it's you.
the one on the left is about 5 years old. So Jeffrey Trang asked about that, and you guys can read this later. And Kevin Carlson answered. And the one on the right is about, I don't know, 13 years old. And David Carchety asked, and Peter Lumsdaine, who some of you guys probably know, answered. And so this, you can read this stuff. Okay. And what else? And I found a paper from 2007. I wish this paper was a little sort of better written. I think if this was a little cleaner, I think people might have picked up on this and did what I was showing here. Okay. I want to get a little crazier for half a second. So Andre Filinsky has a paper called Monads in Action, where he does something called LetEff, and I had the idea of doing this. And the idea is that you're sitting there, you're programming in a language, and then you write a monad in the language, and then you wave a magic wand called LetEff, and that suddenly pushes the monad that you've written into your semantics. Okay, and suddenly it gets sucked into the semantics, and now, like, you wrote the option monad or whatever, and suddenly your language has exceptions. And then you do it again, okay, with like you write a state monad and it gets sucked in, okay? And Andre, I think, gives an operational semantics for this and says that, well, you could implement it by translation, which is what I was showing, but he doesn't really give a denotational semantics for it. And you can actually get it to work using pretty much the same ideas that we were discussing. And so I guess I put this over L, but really I'm just intending to start with a pure language, and then you just do this once. You don't have to pile up layers. And then once you've done this, then you can do this extension from within the language. And the type of expressions are basically things that take, it's kind of a dependent type. They take a return and a let, which are the first two things here in my type of expressions, and they give you back a value of whatever type they are over the monad that you gave. Okay, so it's dependent, right? You see what I mean? The return type isn't over a fixed monad, it's over whatever monad you gave me, okay? And then what LetEff is supposed to do is you hand it a return and a let and an E, which is the body of your LetEff. And then S is the monad that you were previously running over. And then we construct a composite monad, ST, using this recipe here. And then we run E over ST, and this runs. And like some of these things that, like when I was doing this, I was holding my breath when I hit return, because I was like, this works? Are you serious? This is going to work? I can't believe this. 25 years, I did not think this could be done. But I hit return, I'm like, Oh my God, it works. So that's another one that's possibly new, is giving a denotational semantics for this. Okay. One possible application for a LetEff kind of thing is in F#. They originated async and await, which is spread to a lot of other languages for concurrency. And they have a paper called F# computation zoo, where you can do this over different monads. I think that when you nest, nothing happens. Like if you have an async block inside an async block, you should check me on this. And they'll let you do this over different monads, but I think only one at a time. Like you could do any one you want, but just one. And I think when you nest, really nothing happens. Whereas with LetEff, you can actually get this to work, like give me lists, give me writer, give me options. Okay. So I don't absolutely claim this is like actually super practical, but it can be done. Okay. So I'm not seriously proposing that every language from now on should have LetEff in it, but if you're dying to have a extensible semantics, you could. Okay. Let's see. I want to pause for 1 second. One reason why this hasn't been done before, I think, is that nobody cared, because the Haskell people like to have explicit monads, and they don't like to hide them in the back of the semantics. And the ML people, they're satisfied that their language has state and continuations, and I don't know if they have exceptions traditionally in ML. They probably do, I think. Yeah, they do. And they were satisfied, so they didn't need like lots of different monads. So I think the people who care about the stuff that we've been looking at are more programming language semantics people. You know? And I think if more people were interested, this would have happened earlier. Okay. All right, so that's the end of that one. The next part is sort of explaining some of what Andrei Felinsky did. And I think rather than go into that in the next 10 minutes, I think let's jump to some of the craziness and then come back to what Andrei did. So I think I've bored you enough with monads. Okay. And the summary of Andrei's stuff, I'm going to sort of show something I'm calling it continuation monads, which is like a new style of monad or Andrei's style of monad. And they actually can compose as well, and I'll show you the details of that in a bit. But we're skipping over that for now. Okay, so now we start the craziness. I have about 8 slides of craziness. So this is about layers. So layers, I'm thinking about physics, and we talk about the turtles all the way. And so one of the things is like, there's a couple of interesting papers. The first one was Brian Smith's. His father was a famous religion scholar at Harvard, Wilfred Cantwell Smith. And so he was following in his father's footsteps, but he was actually implementing it as code, an infinite tower of interpreters, each one interpreting the next one. And then Wand and Friedman did it using continuations. And sometimes, you know, people say it's turtles all the way down, and is this disturbing or not, right? On one hand, it's the easiest answer because you don't have to explain what happens at the bottom, right, when you stop, because that's another problem, right? So it's much easier in a sense to say it's just an infinite tower.
Sorry,
and
so
now,
Cantwell Smith's tower is like indexed by integers, it's infinite in both directions?
No,
It has a bottom.
no, it has a top, I think. You start at the top and then you can look lower and lower and lower. Yeah. And what's the deal? Now we're used to co-induction, so infinite tower we should be okay, right? It's just it took us a little while to get used to these infinite things, but now we're good with it. So we'll just go with an infinite tower, right? Unless that disturbs you, it's up to you. Let me think. Recipe for a happy life: have happy children. Okay? People are happy if and only if they have happy children. How about that? Okay, that's infinite. Some truth to it. Okay, here's a challenge. So I claim there's a guy in New Jersey who's simulating the entire universe in his basement on a supercomputer, including himself and his supercomputer. I haven't met him, but I'm going to go meet him one day. And so here's a challenge. If you want to make an infinite list, the easiest thing is you take a const cell and you side effect it so that the rest, the cdr, points back to the list itself. There's your infinite list, right? One cell, infinite list. So here's your challenge. Write a simulation. So this would be one step beyond what Cantwell-Smith did. He's got this tower. The way he does it is when you go look, he sort of materializes another layer of interpreters. It's lazy, right? So here, write a simulation that's literally simulating itself. No one's done it, I don't think. You could be the first. Okay, so there's the craziness on turtles. Okay, consciousness. I heard you guys are interested in that. Write challenge, write the simplest conscious program. Okay? By tomorrow. Okay, I just threw that up. Okay, this one, I just wanted to comment on C.B. Aberley's talk, which was the other month, I guess. And let's see. So there are different choices of morphism between toposes, right? In programming language semantics, people are using logical relations a bunch. And they say that two functions, so a morphism between two toposes turns out to be a family of relations. And we say that functions are related if they take related arguments to related results. And people use this all the time now, and people got used to it. And so this is from Reynolds in the 80s, John Reynolds. But it's a little bit of a mystery where the relations come from, because you're starting out and you just have maybe functions. There weren't relations, and then suddenly when you want to get this to do this, suddenly relations get introduced. Possible answer is that if we build the category of toposes by taking a subcategory of the category of allegories, we can maybe inherit the allegory morphisms, which were relations. Okay? So various people, I've heard people when they go to explain toposes, they start with allegories. And, you know, I'm not qualified to say whether that's a good way to start or not, but people do it. And if you do it that way, suddenly you have relations coming in. So it's a possible answer, a possible direction to look in. I just wanted to make that comment. Okay? I don't claim it's an answer, it's a possible answer. Okay? Yeah?
Are these relations like subtyping relations? That's what I remember seeing.
No.
Reynolds' work. Maybe this is a different bit of Reynolds stuff.
No, they're full-on relations. We could talk a bit later. Let's talk later. It would take me a little more time to come up with a good example. Yeah. Okay. Let's see. Here's some possible directions, just some observations of areas where I think I'm disappointed with the state of the art. I wanted to have an ad for relational algebra because I think it's super practical, very usable. Nobody does much of it. I want to encourage people to do more, maybe popularize it more. I think automata theory is ripe for a book using category theory because nobody talks about morphisms of automata. And I think if you were writing an automata book, you could get a lot of mileage of a category of automata. Distributed systems in general, I don't think that the sort of an easy or the simplest or the nicest distributed systems book has been written yet. I'm kind of writing in the best ones I know of here. If you go, distributed systems seems to have a funny thing, which is that once you understand it, you can no longer explain it. Okay? So category theory, there's a lot of good books and they're all pretty understandable. Distributed systems, you will bang your head against the book like, for a long time. And then you understand it and then you can't explain it. Okay, so that's just an ad. I wanted to sort of maybe encourage people to make a dictionary of linear algebra and relational algebra. I claim they're really the same thing, except that, because we talk about matrices of Booleans versus matrices of reals, and I think David wrote some about quantiles and things like that. And make this dictionary for yourself and see what comes out. And I think one of the reasons that people don't connect these as much is that the sort of fundamental operation or the basis for linear algebra is let's apply a linear transformation, whereas the basis for relational algebra is you take two things, maybe A and B, and you say, are they related? And it's sort of like we cross a little bit because those two things are not analogous. There are analogs, okay, but the thing that one focuses on is a little different in the two, okay? And this is sort of maybe part of a program to popularize relational algebra because everybody knows linear algebra. That's taught to undergrads all the time, and hardly anybody knows relational algebra. So I want to sort of encourage more relational algebra. Okay. Why is math unreasonably effective? You have 3 things and you have 5 things and you put them together and you have 8 things. Why did it work? It seems like a mystery at first. Why did it work? Why didn't you get 7 things or 9 things or something like that? Why is math so effective? And I think it's because people are sort of focusing on the wrong instant or the wrong instant of time. You shouldn't be surprised when you get to 8. That's too late. You should potentially be surprised earlier when you decided to apply this theory at all. Okay? So I claim the thing that you might want to, let's just say math is a bunch of patterns, and then, it turns out that nature follows patterns instead of being totally random. So in a sense, the thing that you should be surprised at if you want to be surprised, or the thing that's unreasonably effective, it's just that nature follows patterns. Nature isn't random. And it's up to you whether you want to be surprised by that. Okay. I think this might be the last one, or there might be one more. Here's an explanation of free will. And it's just confusing. I think this is about the illusion of free will. I don't think we have free will, but we all think we have free will. Why do we think we have free will? I think we're confusing causation and correlation, okay? So if I have a robot and I can predict the actions of the robot all the time, I can confuse myself that I'm controlling it. Maybe I am, okay? And then free will is I'm just sort of predicting my own actions. I'm controlling my own robot, okay? So I'm confusing sort of controlling myself with predicting myself correctly. And all of this is speculative, so I'm fully expecting a lot of you to disagree with all of these things. Oh, here's the end. Why is there something rather than nothing? So this guy, Robert Kuhn, has like a PBS show that I only learned about recently on a YouTube channel called Closer to Truth. And they asked this question, which I thought is like the fundamental question. And this question, I think, this is the question that I think there's sort of no getting beyond because I have no idea what an answer would even be in terms of or look like or anything. But surely, if you believe Occam's razor, surely like nothing is the simplest thing. Why? I look around and there shouldn't be an I, there shouldn't be a you, there shouldn't be a universe. If we really believe in simplicity, there should be absolutely nothing, and that should be the end of it. But I look around and there's all this stuff. What the hell is this stuff doing here? It makes no sense at all, okay? Because surely nothing would be simpler. So that's, this This is beyond me. I can make up theories of consciousness all day. I can't even begin to make a theory of why there's something rather than nothing. Okay, that's the end. Okay? Okay?
Yeah.
All right.
Thank you.
Okay.
It is noon, but we have to go. Of course, feel free, and then maybe we'll stick around for some questions or some more discussion.
All right. Okay. I want to, let's see. I want to run through this just in case people are watching.
Maybe we could do a couple questions
And then do that?
we've got a couple. And then
Okay, let's do that.
I just wanted to mention a fair amount of related work to some of what's presented here, which is that they don't call it monad transformers, so you're not going to see it in that literature search, but it goes under the name effect systems. And that all descends from Felinski's stuff. It has a lot of stuff similar to ELET. There's a way to view the earlier stuff you had in terms of free monad translations, or interpretations rather, which then compose, and that's a way to interpret effect systems. Oleg Lisakov has done a lot of the pioneering work in that. Andre Bauer now has a programming language that sort of does similar stuff. And then Nicholas Wu's work on relating that back to monads I think is the most clarifying on how to put it together. But so anyway, there's been a whole fad in effect systems over about maybe the past 7 years, building on Felinski's stuff that's very relevant to what we're presenting. I thought I'd mention that. But he's a better
Yeah, very good.
Nicholas Wu has sort of some synthetic stuff. He had a keynote at a Haskell symposium that was a good, like, historical overview.
Okay, that sounds really good. Nicholas Wu, W-U?
Yep.
Okay, good. And a keynote at the last Haskell?
A couple ago, maybe.
Okay. Okay, yeah, I should definitely compare to that.
So how much does this result about composing translations resolve the issue about, we have no-go theorems for certain distributive laws, right? Like there's non-determinism and probability or something like that don't distribute over each other. There's some paper. So it seems like you can get your translations to compose because you have these parametric monads, right? That like you already define them in every language. So okay, maybe concrete question is like, do you know examples of composing translations where that are cool, where there's no distributive law between the monads?
No, it won't work. The result wouldn't be a monad. There's no free lunch.
No, but
Yeah, the same things that fail would fail here.
right. So I guess that one way of putting that is that monads that don't have a distributive law, you're not going to be able to make them parametric, basically.
You could, but I think when you do this, when you translate one by the other, the result will not be a monad. The laws won't hold. It'll be the same failure that occurs before, right? You can't compose. There's standard results. You can't compose lists that you need your underlying monad to be something.
Commutative is the.
Yeah. So those same problems will pop up. Yeah. No free lunch. So yeah, that would be perfectly good future work to sort of add reasoning about the monads to this. More? No, more?
Yeah, so I had sort of another version of Kevin's question maybe. So thinking back to this cool result from Barr's book that, right, if you can compose monads if one of them's applies the category of the other, and I'm trying to connect that to the story about monad translation. So it seems like what you're saying is that if you write down, your monad just as a program, then you can basically do this translation from some base category to the applies the category of another one, and that's what lets you apply this mathematical result. I'm sort of wondering whether there's a math story for that translation itself. Like, is there a feature of a monad, like perhaps it has some kind of a certain functional form or something that would let you do this lifting from being a monad on some base category to a decisive category?
The translation.
You can think of the language as that's given as a module as being like a syntax tree, and then you sort of take the free monad with regard to that functor, and then that gives you the sort of, you can quote interpret the syntax tree, and that's the reflective capability.
So you're saying that this is a thing that you can generally do with free monads?
You can give a thing that interprets, you can give the syntax as a monad, and then you can give an interpreter for the syntax that sort of freely interprets the freely generated syntax. And then if what you're writing is just parametric over sort of the base thing, but only cares about like the algebraic structure you've added, then that's how you can sort of stack them up. Sorry if that's not my word.
That's not far off. Let's see. There certainly should be a relation between the free monads and like language translations. Yeah, so there's certainly something to be said. Here, the monads that get used are not free, but they're actual monads.
Well, what I'm suggesting is the language module itself that you gave, you can think of as conceptually a free monad over sort of whatever the base is. You can like plug in your elements, like your base types.
Yes.
And then you freely generate the syntax. And then as long as you're only working on the freely added part, you're working with the sort of equational theory of the language.
Yeah, that sounds pretty reasonable. Yeah. Okay, so I just want to put up these slides for sort of reference, and I'm not going to spend time on explaining them. This is an example of Andre's where he's taking list writer and option monads, and we're going to implement this. Okay, it's a crazy cooked up example, but it's you really do have to sort of look in the mirror a little bit if you have to go this far to get examples, but okay. The simplest thing is just you make one monad to do the whole thing, and you add some language constructs, and off you go. It's not modular. The next thing you might do is you might layer this, and you can do this with monad transformers, and you can implement that. What's the API that you might implement? You might have 4 layers. You might have a monad at each layer, okay? And then you can have lifting that takes computations at level 0 and lifts them up to level 1, 1 to 2, 2 to 3. Okay, this is actually quite a nice sort of API for a sort of a stratified monadic system. And you might then have reify and reflection operators, which are, each one is a monad isomorphism. And what they essentially do is they, for example, the first one is an isomorphism between the first level, x1, and a first level computation of an A and a 0 level computation of, say, a list A. And this just reveals that lists are hiding inside x1. Okay? And let's see. And so reify reveals the lists and reflect hides them again. So this is sort of standard, like exposing implementation a little by a little, right? And once you have those, you could say reify 3 times, you could make this run down at the bottom. Okay, so this is actually a nice API for this sort of multi-layered thing. Okay, so one way to implement is monad translation, or monad transformers. Now we're going to sort of go in the direction that Andre uses. So if we interleave the list writer and option monad transformers with a continuation monad transformer, we can do this in even more levels. And it seems like a crazy thing to do. Why introduce more levels? But actually, using continuations, you can get it to run faster because you don't bounce around the levels as much. If you fold your continuation monad into your normal monad, transformer, you can get this, and you can implement using these, which is kind of crazy. But you can. And then we're back to 3, 4 levels just because we've collapsed. Now something crazy happens. You notice that each of these kind of looks like a continuation monad, except that there's maybe some monkey business in the return type. For example, in X1 you have X0 of list in your return type, and in X2 you have X1 of writer in your return type. But other than that, these are really kind of just continuation monads. And the return and let for each of these is actually just the return and let for the continuation monad. And the interesting stuff is actually happening in the reify and reflect. And so what Andre does is he sort of says, you know what, these things are really just continuation monads. And we're just going to kind of use continuation monads instead. And then you get this, and now you notice that the levels no longer refer to each other. And this won't quite type in ML, but you can kind of take the code and you can run it in ML. And you can do this, and you have reify and reflect for each level. And that's the end of it, and then you can run the example I gave at the beginning. And if you look at this, you look at, for example, reify and reflect for level 3. It doesn't reference reify and reflect for level 2 or level 1 at all. They really are independent, okay? The place where they get tied together is in this run operator, which sort of chooses what order to put the levels in, okay? And so I'm sort of calling this continuation monads, and this is what Andre does. And if you think this is a little bit hard to understand, you should go and read Andre's papers, and then you will reset your idea of what hard to understand is, especially representing layered monads. But this is a piece of code you could run, okay, and play with. Okay, so, all right.